This video is part 4 for section 7.4 of Math 311, course in linear algebra at Western Illinois University. So we are going to continue. We talked about the idea of a pseudo-inverse. We did one example. I'm going to do another example right now, and I'm going to see if this light above my head is distracting. I'm going to turn this off. So hopefully you can still hear me, even if you can't see me. Okay. So now here we have a 2 by 2 matrix A, and the first thing that you should keep in notice is that the rank of this matrix is 1, right? Because the rows are multiples of each other, the columns are multiples of each other. So this is not invertible, and the rank is not 2; it's equal to 1. All right. Well, we can see we're going to still see that we can not only will the pseudo inverse exist, but it will actually have will be a little useful. So let's look to find the pseudo inverse again. Let's start with computing A transpose T. We can see in this case M and N are both equal to 2 in this case. So this is actually symmetric, so A transpose A they're equal to each other. Won't always be the case, but and this turns out to be 5, 10, and 10, 20. Okay, so to find the eigenvalues, take the determinant of 5 minus lambda, 10, 10, 20 minus lambda. It's going to be 5 minus lambda, 20 minus lambda, minus 100. And if you multiply this out, this is going to be lambda squared minus 25 lambda plus 100 minus 100. So this is the characteristic polynomial. This factors very nicely. And we can see that the eigenvalues will be 0 and 25. So we'll let lambda 1 be 25, lambda 2 be 0. So sigma 1 is the square root of 25, which is 5, and sigma 2 is 0. So those are the singular values. To find the eigenvalues, when lambda is equal to 25, we get minus 20, 10, 10, and negative 5. And hopefully you can see it's not too hard to find that the vector 2, 1 is orthogonal to both rows. All right. No, it isn't. No, it isn't. So, sorry, it's 1, 2, 1, 2, 1, 2. So let's have Professor correct that. It's 1, 2. Okay. And so 1, 2 can be normalized. It has length 5, right? Or the square root of 5. So we can divide the entries by square root of 5. And we get this. Okay. Now if we take lambda equal to 0, plug that in here, we get 5, 10, 10, 20. And this time our, let me get this right, the eigenvector will be 2, negative 1. Hopefully you can see that works. Once again, the eigenvector, the vector has length 5, so we can normalize it by dividing by the square root of 5. Okay. All right. So we got 2 square root 5, negative 1 square root 5. And then we take these, and those are our columns of V. So we have 1 over square root 5, 2 over square root 5, 2 over square root 5, negative 1 over square root 5. Okay, so that's V. Next, we can, to find U, U1, this will be 1 over sigma 1 A V1. So this is going to be 1/5 times A times V1. Okay. So we got 2 over, we get that, and then this will be 1/5 times, well, this will be 1 over square root of 5 plus 4 over square root of 5. That's 5 over square root of 5. And 2 over square root 5 plus 8 square root of 5, that's 10 over square root 5. And when we multiply this by 1/5, this just becomes 1 over square root 5, and this is going to be 2 over square root 5. Okay, and coincidentally, this is actually the same vector as here. Okay, so interestingly, u1 and v1 are the same. Now we can't go to u2 because the rank in this case is only 1. So remember how to find u2. We want u2 to be a vector orthogonal to u1, and by chance we already know that this vector is orthogonal to this, and this is also a unit vector. So u2, we can just take u2 to be v2, and so u2 will be 2 over square root 5 negative 1 over square root 5. Remember, the whole idea was to extend u1 to an orthogonal basis of R2, and we know that this will certainly work. Okay, so believe it or not, in this case, u and v are going to be the same matrix. Okay, and sigma is going to be 5, 0, 0, 0, and sigma plus will be 1/5, 0, 0, 0. So the pseudo-inverse of A is going to be V times sigma plus times U, or I should say U transpose, but because U is this matrix is symmetric, U and U transpose are going to be the same thing. So this is going to be okay. All right, and then when you do the arithmetic, when I computed this turned out to be 1 over 5 square root 5. 2 over 5 square root 5, and then this was 0, this was 0. Okay, so the actual result turns out that A plus was equal to 1/25, 2/25, right, and then yeah, 2/25. I might have miscopied it. Let's see. Did I make a mistake? Here, let's see. So this is 1/25, right? And then this is 2/25, right? And then this is 2/25. Okay, and then this was 4/25, I hope. Let's see. Yeah, 4/25. Okay. All right. I hope I didn't make. I hope this should be the right answer. Okay. This should. Yeah. Check it. Okay. But I think I caught my mistake. All right. So now, how can we use this here to help? What good is this for? Well, we can remember with least squares, finding the least squares, we were able to find the least square solution as long as our original matrix A, as long as the columns of A were all linearly independent. Well, what if we wanted to find a case where, let's say, if we wanted to find, let's say, AX, if we wanted to find minimize AX minus B in this case when A is this matrix, and how can we still find an X for which this is as small as possible? And the answer is yes. Okay, so let me just show you where the pseudo inverses come in. Come in here. And so how does this work? All right, so once again, we want to do this. So in this case, A again is an m by n matrix, letting B be a column vector in Rm and X is a column vector in Rn, and we want to minimize the least squares problem is we want to minimize the length of Ax minus B. Well, how do we do that? We can do that. That's the same thing as minimizing the square of the length of Ax minus B. Now, because U is orthogonal, U transpose is also orthogonal. So when you multiply a vector by an orthogonal matrix, it doesn't change the length, right? So multiplying by U transpose doesn't change the length. And then in that case, when that happens, U transpose A, well, U transpose A is the same as U transpose U sigma V transpose. Okay, so the U transpose and the U cancel out, and we just get sigma V transpose. So that's how we get this, and then we distribute the U transpose, and we get U transpose B. All right, now we're going to make a little substitution here. We're going to let V transpose X be equal to Y, and we're going to let U transpose B equal C. And so after this substitution, we get this is equal to the length, the square of the length of sigma Y minus C. All right, and again, you can check that the dimensions are still okay. For example, Y is still a column vector in Rn, and C is a column vector in Rm. Okay, so now if we examine this difference of these two vectors a little closely, sigma Y, because sigma has so many non-zero entries, sigma Y really just consists of these. The first R entries are just sigma 1, Y1, sigma up to sigma R, YR, and then everything else is 0. And then, the entries of C, I just labeled them C1 through Cm. Okay, so if we're trying to minimize this, so if we take the square, if we subtract these, and then take the square of the result, or the square of the distance of the result, we get this. We take y1, sigma 1 y1 minus c1, we square that, and then all the way up to sigma r yr minus cr, square that, we add all this together, and then we just get 0 minus cr minus 1 squared. That's just cr plus 1 squared, so on, all the way to cm squared. Now, keep in mind that these are fixed. We can't control these. These are fixed because they're completely dependent on B, which was given to us, and U transpose, which was dependent on A, which was given to us. The only thing that's changed, the variable here, is the y's, right? So our idea is, if we want to minimize this whole thing, we can only minimize this. And we can minimize this by setting this equal to 0. The only way this can be 0 is if all these differences in the parentheses are all 0. Okay, so they're minimized when sigma 1 y1 equals c1, all the way up down to sigma r yr equals cr. And then dividing through the sigmas, which we can do because they're not 0, this tells us that y1 is c1 divided by sigma 1, and y sub r equals cr divided by sigma r. So what this tells us then is that we can write this equation that this column vector y is equal to, can be written this way as just this matrix 1 over sigma 1 through 1 over sigma r times c1 through cm. Okay, this basically corresponds to this equation, right? This system of equations right here. But then we can multiply. But remember that y is just v transpose times x, and c is u transpose times b. And in fact, this matrix, we can multiply on the left both sides by v, and they'll cancel out. And this matrix is none other than our sigma plus. We have the reciprocals of the singular values right here. So we get that X is equal to V sigma plus times U transpose times B. And what is this? This matrix is none other than A plus, our pseudo-inverse. So X is going to be the pseudo-inverse of A times B. All right. So, and that gives us to our the main result here is that the solution, the least squares solution to AX equals B is X equals A plus times B. Okay. And of course, obviously, when A is just an irregular invertible square matrix, this is the A plus is just A inverse. Okay. So if we just wanted to go back to our the example we just did here, let's say if we wanted to find the least square solution to in this case 1, 2, 2, 4 times let's say xy equals, let's say 3, 5. We would just take our inverse here. So we would just take xy would be 1/25, 2/25, 2/25, 4/25 times 3, 5. And this would be, let's see, so 3 plus 10, that would be 13/25. And this would be, let's see, 6 plus 20, that's 26. So this would be 26/25. Okay. Assuming I did everything right here. And so that would be the least square solution. So this would be the value that minimizes minimizes the length of AX minus B. Okay. So those pseudo-inverses, I'll just put this, I'll pop back in here. Hello again. Pseudo-inverses are pretty useful. The least squares method, you can use it whether the matrix has full rank or not. So hope you enjoyed this lesson, and hopefully those of you who are engineers will use this later. Thank you.